Hello, it's Miss Austin, and I'm going to be doing the lesson one practice problems in case you struggled at all. I know there was an answer key, but answers aren't everything. Knowing how to do them is more important. So here we go. Number one, it says a rectangular schoolyard is to be fenced using the wall. Let that zoom in of the school for one side and 150 meters of fencing for the other three. I'm going to draw a picture of this. So here's the school. And apparently they're putting a fence in like this around. And this is taking up 150. And it says, so the length, so if I call this X, right, then this is also X because it's a rectangle. And they told me that I had 150 meters of fencing. So how much is left? 150 take away these two, whatever this is. If this was 10, then I took away two of these, two tens. If this dimension is 20, then I took away two 20s. Whatever it is, I'm taking away two of those. Okay? So write an expression for the area. How do you find the area of a rectangle? You do one dimension times the other. So I'm going to do this. The area of this rectangular, what's this called? A schoolyard. So this dimension times this dimension. That's a polynomial, sort of like the one in lesson one. What is the area of the schoolyard when x is 40? Well, if I let that be 40, I can just plug it into my formula. 40 times 150 minus 2 times 40. Imagine if, right? 2 40s is going to be 80. So 40 times 150 minus 80. Whoops, running out of room. So 40 times, that'd be 70. And I mean, you could do this without all this math. Look, if this is 40, right? And 40, that's 80. And if what's 150 take away the 80? 70. Now multiply those two together. The total area of this is 2,800. What are we in here? Square meters. What is a reasonable domain? What are numbers that you can plug in for these dimensions? Well, the smallest you can have is 0, right? Or, you could have a half, 1, 1.5. So I'm going to put 0 over here. So I want x has got to be bigger than 0. And then realistically, how big could I make these sides? Sorry, guys, I'm trying to get this to focus a little bit better. I'm going to turn off this light behind me and see if this helps. And turn on this light. Yeah, it's a little bit better. Well, if I did, I have to have enough fence for right here. So, you could problem solve this. You could just keep thinking, right? I can't have this dimension be 0. So how big could these be? And I would still have some left here. I mean, think 50. 50 and 50 is 100. So I'd still have some left. What number would get this down to 0? That's pretty much what you're asking. 150 take away 2 of what's going to make 0? You might be able to just problem solve this out in your head. 75. 75. If this is 75 and that's 75, that makes 150. And 150 take away 150 leaves nothing left. So I'm going to put that as my upper bound. I'm not going to say it could equal 75 because then you wouldn't be able to have any schoolyard. But anywhere from 0 up to 75. Those are numbers that would make sense in this problem. Number 2, Noah finds an expression v of x that gives the volume of an open-top box. Remember the problem if you watched my other video. Here's the box. In cubic inches in terms of the length x in inches of the cutout squares used to make it. This is the graph Noah gets. So remember when we typed this in, if you watched me do the lesson, if you go to Desmos and type in the expression, this is what Desmos shows. This part of it doesn't really make sense, right? It's right here. This is the volume getting bigger and bigger and bigger. There's the max, and then the volume gets smaller and smaller and smaller, and then this model doesn't really make sense anymore, okay? So it says this is the graph Noah gets if he allows x to be any value between -1 and 5. That's how much you're cutting out, between -1 and 5. What would be a more appropriate domain? Well, first of all, x is how much I'm cutting out of the corners. -1 makes no sense, right? I think a more appropriate domain would be no cutout all the way up to 5. Actually, you don't even need to go to 5. Just looking at this graph, I can tell the max occurs right here, and then right? I mean, once I get to like 2.5, so maybe 3. 0 to 3 is all I really need to look at to see this problem. Not even 3, you could say 2.5. What is an appropriate maximum volume? There's the max right there. And what do you think? I don't know. I'd say like 14.9, or you could say 15. This is inches. Again, if you didn't watch the video about the lesson, this is what happens when if you cut out some random amount of the corner, and then on paper, if it's an 8.5 by 11, it was like this. You take away 2 of whatever that cut is from each dimension. And when you multiply the length times the width times the height, this is the graph you get. And this right here is a polynomial. That was number 2. I thought maybe there was more to that, but maybe not. Nope, we're good. All right, number 3. Maya wants to make an open top box by cutting out corners of a square piece of paper or cardboard and folding up the sides. The cardboard is 10 by 10. Imagine this is what it looks like. Right? And then you cut out the corners. And then when you fold it up, once you cut those corners out, you get a box. An open top box. Okay. The volume V of x in cubic centimeters of the open top box is a function of the side length x in centimeters of the cutouts. That's the cutout. Here's how big the paper is. You're going to keep getting this question asked all unit. So it's helpful to understand, right? Imagine here's your paper, 10 by 10. Every time, however big this is, you're going to take away 2 of those from each dimension. So it doesn't matter which dimension you put first. You might start to just memorize however big the cut is times how big's your paper. You take whatever this dimension is, take away 2 of those cuts, 1, 2, times the other dimension. This one, it happens to be the same. It's a square piece of paper. Take away 2 of those dimensions. Length times width times height. The only thing that changes in this polynomial is the size of the piece of paper. Those 2 numbers right there. The one we did in the lesson was 8.5 by 11. If you look at the lesson summary, I think they did like a 3 by 8 piece of paper. You would put 3 and 8 here. You're still taking away 2 cuts off of each dimension. What is the volume of the box when x is 3? Well, we're just going to plug 3 in. We're going to put a 3 wherever we see x. V of 3 is 3 times 10 minus 2 times 3 times 10 minus 2 times 3. So that's 3 times, we could do this in our head. What's 10 minus 6? 4. That's going to be 4 again. 3 times 4 is 12. 12 times 4 is 48. We're in centimeters, and this is volume cubed. Number 4, the area of a pond covered by algae is 1/4 of the square meter on day 1, and it doubles each day. Complete the table. All right, day 1, 1/4 doubles. So if I times that times 2, I get a half. Doubled 1, doubled 2, doubled 4, doubled 8. That's it. Number 5, here is a table showing values of sequence P. Define P recursively using function notation. All right, so recursive, I give the first term. So P of 1 equals 5,000. And then to get any term after that, I take the previous term. I'm just getting that all ready. I haven't even figured out what's going on here yet. What's happening as I move from one term to the next? Dividing by 10, which is the same as multiplying by 1/10, right? On sequences, we want to talk in terms of multiply. So I multiply by 1/10, and that's for n greater than or equal to. I already gave the first term, so I'm going to start on term 2. I think I skipped this one, so that's a wrap. I did 1 through 5. So I'll be back for another video. I hope that helped. See you soon.